In 5.2, we're going to focus on the uniform random variable and its distribution. This is one example of a continuous random variable. It's defined by two things. One is that it has a smallest value and a largest value. The smallest value we denote with an A, the largest value we denote with a B. And all the outcomes in between that smallest and largest value are equally likely. All right, if we want to define a random variable x as uniform, we use a u to stand for the uniform part. And then the two values that uniquely define it are that smallest value a and the largest value b. So that's comparable to the values n and p that we use for binomial. Okay, each distribution is defined by unique characteristics. So binomial was defined by n, the number of trials, p, the probability of success. Uniform is defined by a and b, the minimum and maximum value. The graph of the PDF for uniform is a rectangle. We saw that in the previous section a little bit. And if we sketch a graph of that, we've got x on the horizontal. The vertical gives us f of x. And we go from that minimum value a to that maximum value b. And the graph is constant between those two values. So that's how we get that rectangle. All right, the other thing that we learned about continuous random variables is it's defined by this probability density function f of x. And to find f of x for uniform, it's the easiest one to find for a continuous random variable. You just take 1 divided by b minus a. So the height, you can also think of that as the height of the rectangle. That's actually 1 over b minus a. Okay. Mean and standard deviation for uniform. We remember for binomial, we also had a unique way to find the mean and standard deviation. Now we're going to define it differently with a different random variable. To find the mean, this might just come sort of intuitively, but we're going to basically take the average of a and b. So we add those two together and divide by 2. Standard deviation is not intuitive. It is the square root of b minus a squared, and then that's over 12. Okay, so that's not one you're probably just going to come up with if you don't have your formula sheet handy. So just make sure you remember standard deviation is something that you're going to want to look up. So how do we find probability of a uniform random variable? It's a continuous random variable, so like we said in the previous section, we're always going to find probabilities of a range. So we find, and then the other piece is that probability is the area under the curve. So if we've got our distribution function graph here going from A to B, all right, where the height is this value f of x, all right, to find the area under the curve from C to D, okay, we want this shaded area here. That's the probability we're looking for. For a uniform distribution, all right, we can see that it's basically a height times a base. It's a rectangle, that area. So we can sort of use geometry to think about how we're going to find this area. So the height is, you can see that matches up with whatever that f of x value is. And the base is the difference between D and C. So that's what we have written here. And really what we're doing is we're finding the area of that rectangle. Let's look at an example. The amount of time in minutes that a person must wait for a bus is uniformly distributed between 0 and 15 minutes inclusive. Let x be the amount of time waiting. Let's define the distribution for x. Well, we're told that it's uniform, so we can put that u in there. And now we want to put in the minimum time and the maximum time. So just remembering that this first space is going to be a, the minimum, and the second space is going to be b, the maximum. So it says it goes from 0 to 15. Now we have what we need to find f of x. Okay, just that's 1 over b minus a. So in this case, 1 over 15 minus 0. So 1 over 15. So for a uniform random variable, f of x is always just going to be a constant. It's going to be a value. It's not going to have x in it. All right, so let's graph this distribution. All right, we have x along the vertical. We're going out to 15. All right, we're starting at 0. All right, I guess I can label that too. And the height of that rectangle is 1/15. Okay, so there's the graph of our PDF. All right, so now let's find a probability that an individual waited between 4 and 8 minutes. So if we write that in probability notation, we're looking at the probability that 4 is less than x is less than 8. And if we want to draw a picture, which can be really helpful to kind of visualize this. All right, we are going from 0 to 15. All right, this is 1/15. We want to go from 4 to 8. All right, so just a little sketch here. Say we're going from 4 to 8. We're looking for this shaded area. Okay. From our notes before the previous page, we said what we're going to do is we're going to take f of x times d minus c. Okay, but hopefully you're recognizing that that's just the height times the width. So the height is the 1 over 15, and the width or the base is 8 minus 4. So we get 4/15 for that probability. And if we find the decimal form and round to 4 decimal places, we're going to get 0.2 repeating 6. So rounding that to 4 decimal places, we get 0.2667. Okay, let's look at the next one. Find the probability that the individual waited more than 10 minutes for a bus. So in probability notation, that's going to look like probability that x is greater than 10. Now it's only defined up to 15, so we don't have to write it like this, but we can also, to remember that we got that 15 in there, it's the probability that x is in between 10 and 15. It's always okay to draw a picture to just visualize what it is we're finding. So we want greater than 10. So we're looking at this area right here. Oops, let's see. I don't know where I got that 1/4 from. Let's fix that. That should be 1/15. Okay, so this probability then is going to be f of x, all right, or the height, 1/15 over 15 minus 10. So 5 over 15, which is 1/3, which if we write that in decimal form to 3 decimal places, we get, 0.3333. Now let's find the mean and standard deviation. So the mean, just a refresher, it's basically we're taking the average of the min and the max. So in this case, we got 0 plus 15 divided by 2. So that's 15 divided by 2. So we get 0.75, and we can label it as minutes. Okay, standard deviation, this is that one that doesn't come quite as intuitively. We take b minus a, square it, over 12, and then we take the square root. Okay, why it's written like that and not like what I think is a simpler form, where in the numerator you're taking the square root of something squared, so those undo each other. So that's just like having b minus a over the square root of 12. So you can kind of skip a little bit of a step there. All right, so we're going to get 15, all right, minus 0, which is just 15 over the square root of 12. That's going to give a standard deviation of 4.33. And that has the same unit, so we can label that as minutes. Okay, one more probability with this example. Suppose it is known or given that the individual waited more than 5 minutes. What is the probability that they waited more than 10 minutes? So we can write this in probability notation. This is a conditional probability. So we're wanting to know the probability that they waited more than 10 minutes. So x greater than 10, but we're given that they waited more than 5. Okay, from our probability chapter, we have a formula that we could use for this particular type of probability. I think it's easier if we draw a picture of what we have here. Okay, so we're going from 0 to 15. Right, our height is 1 over 15. And what we're given is that x is greater than 5. So if we've got 5 right here, we are given that this has happened, okay? That has occurred. Okay, so we have shrunk. We can think of it as shrinking it from the 0 to 15. Now it's to the 5 to the 15. And now what we want is the probability that x is greater than 10. So, all right, here's 10. So here is the area. This is the probability that we want, that area. Okay, so we can kind of see, to get that probability, instead of multiplying by that 1 over 15, which is the difference between 0 and 15, we want to divide by the difference between 15 and 10, okay, because that's what's given. Okay, so now we're shrunk down to 10 from the 15, and then we are going to use that in the denominator. So we can think of that as taking 15 minus 5 in the denominator, and in the numerator we have got 15 minus 10. Okay, so instead of using the 1/15th, we're replacing that by using like 1/10. Okay, so dividing by 10 is like multiplying by 1/10, and then the difference between the 15 and the 10 is 5. So we get 5/10 or 1/2 or 0.5 for that probability. Let's look at another example. According to a study by Dr. John McDougall of his live-in weight loss program at St. Helena Hospital, the people who follow his program lose between 6 and 15 pounds a month until they approach trim body weight. Let's suppose that weight loss is uniformly distributed. We are interested in the weight loss of a randomly selected individual following the program for 1 month. Let x equal the weight loss of a randomly selected individual. Round probabilities to 4 decimal places. So let's start off by defining x. Right, so we're told that we've got uniform weight loss. So it's uniform, and we're going to define it by the min and the max value. So the min is given to us as 6 and the max is 15. And we want now f of x, and that's 1 over the max minus the min. So we get 1/9. And we look at a graph. Okay, we're going from 6 to 15, and the height of the rectangle is going to be 9. So there's our PDF graph. Okay, let's find the mean weight loss. We're going to take basically the average of the min and the max. So 6 plus 15 over 2. So we get 21 over 2, which is going to give us a mean of 10.5 pounds. Okay, now we want to look at standard deviation. So I'm just going to write the way that I would approach it. Let's just go b minus a over the square root of 12. So 15 minus 6, we get 9 over square root 12. And that gives us a value of 2.59, etc., which if we round to one decimal place or two decimal places, we get 2.6 pounds. Okay, let's find this probability. We want the probability that the individual lost more than 10 pounds in a month. So that's x greater than 10. And just remembering that we're going to take f of x times, d minus c. In this case, we're only given one value, so we have to remember that, well, we know what f of x is 1 over 9. That our d, if it's not given to us, it's going to be that max value. So 15 minus 10. So we get 5/9 for the probability, which is repeating fives. So if we round that to 4 decimal places, 0.5555. Okay, we have another conditional probability. Suppose it is known that the individual lost more than 10 pounds in a month. Find the probability that he lost less than 12 pounds in 1 month. So the probability that we're looking for is that x is less than 12, but we're given that x is greater than 10. Okay, so if we want to draw a picture, right, we have 6 to 15. That's 1/9. And we're given that it's greater than 10. So we know we're dealing with just this piece of the rectangle. Okay, so that's what's given, that piece right there. And now we want probably the x is less than 12. So let's call that 12. We just want that part right here. Okay, so that is the area we're looking for. Okay, so we're given that it has to be between 15 and 10. So the denominator is going to be 15 minus 10. And then what we're looking for is if it's greater than 12, but also, I'm sorry, less than 12, but also greater than 10. So in the numerator, we have 12 minus 10. All right, so we get 2/5 or 0.4. Okay. The next thing is a little bit different. Okay, let's look at this next one, which is a little different than what we've been doing. I want to make one change to the question. And here it is, 20% of individuals lost. I want to change this to less than how many pounds? Okay, a couple hints are given here to answer this. State this in a probability question, draw the picture, and find the value. So let's start with the picture. All right, here's our PDF going from 6 to 15. And now let's try to visualize what's being asked here. 20% of individuals lost less than how many pounds? Okay, so that number is a number that we don't know, this many pounds. So let's call it K pounds. Okay, and we can just, it's going to be somewhere between 6 and 15. So let's put it right here. Now, the piece of information that we do know is that there's area of 20% underneath the curve, underneath the rectangle between 6 and k. And remember, we've got the height here is 1/9. Okay, so now let's write the probability statement. So it's saying, what is the probability that x is less than k? And we know what that probability is. It's 0.2. So the piece that we don't know is the k. But we know how to write down this probability. So that probability is 1/9 times the difference between k and 6. And that's equal to 0.2. So we have a little algebra problem. We need to solve for k. Let's multiply both sides by 9 to get rid of that fraction. So we're going to get k minus 6 equals 1.8. And then we add 6 to both sides, so we get add 6 to both sides, so we're going to get 7.8. Okay, so the k pounds here is actually 7.8 pounds. So we could say 20% of individuals lost less than 7.8 pounds. Okay, let's look at this one. 60% of individuals lost less than how many pounds? Okay, we'll again use the k to stand for that number of pounds that we're looking for. And if we draw the picture of the density curve, going from 6 to 15 with f of x equaling 1/9. So what we're looking for is a k value such that less than it is 60%. So k is going to be somewhere around there. And we know that this area right here is 0.6, is that area. So we can write the probability statement. The probability that x is less than that value k is equal to 0.6. And then replacing that probability notation with how we find probability, we're going to take 1/9 times the difference between k and 6. And then that's equal to 0.6. All right, so multiplying both sides by 9, we get k minus 6 equals 5.4, and then adding 6 to both sides, we get k equals 10.4. So we can say that 60% of individuals lost less than 10.4 pounds. All right, let's look at the next one. Find the 75th percentile, and then we'll want to explain what that means. So again, let's start with a picture of the density curve. And 6 to 15 gets a little after a while, but it really does help figuring out how to do it. So 75th percentile, we got to go back, remember what that means. That is the value that has 75% of the data values less than it. Okay, so it's going to be, some value here. Well, again, we'll call it k, and it's the 75th percentile, so this area is 0.75. So we can write down the probability statement that x is less than k, probability that x is less than k is equal to 0.75. So replacing that probability notation with how we calculate the probability, 1/9 times k minus 6. This looks exactly like the one above, but we have a different probability. All right, multiply both sides by 9. We get k minus 6 equals 6.75. And then adding 6 to both sides, we get 12.75. All right, so if we want to write down what that means, if we say the 75th percentile is 12.75, that means that 75% of the participants in this program lost less than 12.75 pounds. All right, one more with this example. Find the probability that the individual lost between 3 and 9 pounds in a month. All right, so you can start with the picture. And we're looking for the probability that X is between 3 and 9. Okay, so this is how it can be helpful to draw the picture, because we can realize that this value 3, right, is somewhere over here. And there's no, the density curve stops, or it starts at 6. So 3 is not a valid value for this probability distribution. So what we want to recognize is that what we're really looking for here is the probability that X is between 6 and 9. Okay, because there is no area above the values 3 to 6. In other words, that probability or that area is 0. So this probability statement really becomes the probability that X is between 6 and 9. So we can find that probability. We take that 1/9, multiply it by 9 minus 6, and so we get 3/9, or 1/3, or 0.3333. Okay, one more example, and I hope, as always, if you want to work through these problems on your own and then come back and watch, then you can kind of check and see if you're on the right track and getting the same result. A fireworks show is designed so that the time between fireworks is between 1 and 6 seconds and follows a uniform distribution. Okay, first question, find the average time between fireworks. So kind of going back to that mean value. So just a reminder, we're going to take A plus B, the min and the max, add those together and divide by 2. It just really is an average. So we got 1 plus 6 over 2, 7/2, or 3.5 seconds. Using that same distribution, find the probability that the time between fireworks is greater than 4 seconds. Okay, draw the picture. And our f of x, all right, we got to remember that's 1 over the max minus the min, so 6 minus 1, so we get 1/5. So that height of that rectangle is 1/5. We go from 1 to 6. We're looking for the probability that x is greater than 4. So we want this area, the area of that triangle, so taking 1/5 times 6 minus 4. All right, we get 2/5, or 0.4. Okay, let's look at part C. Find the probability that the time between fireworks is between 2 and 5 seconds. All right. I got going from 1 to 6, and the height is 1/5. And we want probability that x is between 2 and 5. So going from 2 to 5, we want that area. Hopefully this is becoming pretty routine for you. So we get 5 minus 2, which is 3 times the 1/5, so 3/5, or 0.6. Okay, next one, 25% of wait times is more than how long of a wait time? So state this in a probability question, draw the picture, and find that value of x. Okay, so we got the same old distribution here. And we want the probability that x is greater than some unknown value k equals 0.25. So we put k here. The area or the probability that we are given is this shaded area. It's 0.25. So replacing that probability notation with how we calculate that probability, 1/5 times 6 minus k equals 0.25. So we multiply both sides by 5, and we get 6 minus k equals 1.25. And then here, if we think about adding k to both sides, that makes the k positive, and then subtracting the 1.25 from both sides, we get k equals 4.75. And we'll want to label that. It's time and in seconds. This next question, what is the median of x? We did not go over this as far as like a characteristic or a property of the uniform distribution, but we want to kind of think about all the things that we have learned and kind of pull from that to answer this question. So there's a couple ways that we could answer that question. We have to think about what we know about the median. The median is the value that is the middle value. Okay, and specifically 50% are 50% of the values are less than the median, and 50% are greater or more. Okay, so that would be one way to approach answering this question. Okay, so we could do something like we did above, but use 0.5 instead of 0.25, and that would answer it. But there's actually a simpler way to think about this. When we looked at the comparison of median and mode and mean based on different types of distributions, we had conclusions about the relationship of the mean and the median, depending on the shape of the distribution. Well, if we look at the distribution of the uniform, and we want to decide, well, what is it? Is it symmetric, skewed left, skewed right? I think that we're all going to conclude that we've got a symmetric distribution. It is even on both sides. Okay, so what did we say about the mean and the median for symmetric distributions? Well, symmetric distributions have the median equal or approximately equal to the mean. We already calculated the mean, which was 3.5. Okay, so that is the exact same answer that we would get if we went through the process like we did up in the previous one using 0.5 instead of 2.25. Okay, that's it for chapter 5.